The directions for all of these examples is going to be to solve for x. So in this example, the first thing you want to ask yourself is, where is the x? The x here is in the exponent, which means we're working with an exponential equation. When you're solving for x in an exponential equation, what is it that you are supposed to do? Well, there's two rules that we'll be working with on the examples in this lesson. The rule we'll use for this one is, when x is in the exponent, use a logarithmic equation. We're going to use a logarithmic equation because it's the inverse of an exponential, and it will get that x alone for us. If we're going to use a logarithm, that log will have a base. It will have the same base as our exponential. The base is 2. We're going to take log base 2 of both sides. When we take the log base 2 of 2 to the x power, since they are inverse operations, you need to think of this as you would think of the square root of x squared, or 1/3 of 3x, or x plus 5 minus 5. Inverse operations allow things to sort of clean up, go away, disappear. So in this case, a square and a square root, you might think that they cancel out. 1/3 and 3, they reduce down to 1. Plus 5 minus 5 gives us 0. In each case, we're left with just x. When we use log base 2 with the 2 to the x, you have to remember that this is the inverse of this. Log base 2 is the inverse of 2 to the x. If it were a 15 to the x, we would use log base 15. Inverse operations work the same way all the time. We have a square root and a square, times 1/3 and times 3, or divided by 3 times 3. Add 5, subtract 5. In every single example, the only thing that you would be left with is the x, because each operation and the inverse operation cancel one another out. So in this case, it's no different. Log base 2 and 2 to the x essentially go away, and we're left with x equals. On the right-hand side, the only thing we'll be left with is log base 2 of 3. Now this might not seem finished, but it is. This is completely done. We have no variable over here. Log is an operation just like a square root. We were allowed in the past to leave an answer as something like x equals the square root of 7. In fact, that was encouraged because this was an exact answer. When you use a calculator and round, that's actually an approximate answer. So this is better. If I leave something in terms of log, it's going to be more precise, it's going to be exact, we aren't rounding. If you use a calculator, you'll be rounding, and that's what we call an approximate solution. Now, before we go on, I just want a couple other ways to think about this. I think that what we just did here is the easiest, cleanest way to do this problem. Some people, however, may show it to you differently in the future. So, if you thought of this as b to the y equals x, you can change that from exponential to logarithmic form. That rule is still applying. When x is in the exponent, use a logarithmic equation. So we just change it to logarithmic form. Take this form, and we change it into y equals log base b of x. If we swap every piece out for where it is, what will we get? The y is the exponent, which is x, equals log. The base is 2. X was the thing alone over here, 3. If you think of it this way, this thought process, you get the exact same answer as what we got right over here. Another way to think of it, if you start off by taking log base 2 of both sides, if we apply the power property right now, where will this x go? It would go right in front. X times log base 2 of 2 equals log base 2 of 3. Do you remember what log base 2 of 2 equals when the base and the thing you're taking the log of are equal? Or do you remember what to ask yourself? 2 to what power is 2? This whole expression equals 1. X times 1 is just x, so what are we left with? Well, third time, x equals log base 2 of 3. So there's your solution. Now let's try a different one. Here again we have an x and an exponent, and the rule is the same rule. when x is in the exponent, use a logarithmic equation. However, before we can use a logarithmic equation, we need to isolate the base raised to the power. I need this piece to be alone. My exponential equation, b to the x, has to be alone before we can implement log. How do we get this alone? With some different inverse operations. We're going to start off with subtraction and subtract 8 from each side. 10 to the x equals 1,000. Now that we have our exponential expression alone, we can take the log on both sides. We would take a log with a base of 10. We don't need to write log base 10 because log base 10 is actually plain log written alone. It's also known as the common log. Here, if you'd like to do it the first way I showed, you kind of just cross those out and you're left with just an x. The right-hand side, though, we can simplify, whereas before we could not. The last question we did was log base 2 of 3. If I asked myself 2 to what power is 3, I wouldn't get a nice answer. I wouldn't get an integer. I wouldn't even get a nice rational number. Here, however, 10 to what power is 1,000. Final answer? Great. Our third example, we have 14 to the x plus 1 equals 36. The last example, we had to get rid of an 8 that was out front, separated from the b to the x with an addition sign. Here, I do have my base raised to the power, but it's really already alone. I don't need to bring anything over before I go and switch up and use log. So now I'm going to take the log of both sides. What base should the logarithm have? The log should have a base of 14, the same as the exponential. Log base 14 of 14 raised to the x plus 1. Now you may think of it the way we did in the last two examples where we can just cross it out, but let's switch it up a little bit this time, okay? This time I'm going to bring the x plus 1 out front using the power property. X plus 1, when you bring something like this out front, it is critical you put it in parentheses, otherwise your operations will be misleading. X plus 1 times log base 14 of 14. Log base 14 of 14 equals 1. Because 14 to what power is 14? The answer is 1. Now we really only have one more step left to get x alone, and we can do this next step in two different ways. We're going to subtract 1 from both sides, but where we put it on the other side does kind of matter. If we subtract 1 on each side, x will equal, you may choose to write it as log base 14 of 36 minus 1, or negative 1 plus log base 14 of 36. If we write it like this, people tend to make a mistake here and combine 36 and negative 1, which would be wrong. That's why you'll often see multiple choices where they'll give it to you written in this order instead, because by having negative 1 plus log, you will be less inclined to make a careless error and combine that negative 1 with 36. They're not like terms, so you can't combine the negative 1 with the log base 14 of 36. You can only combine log base 14 of 36 with another log base 14 of 36. So if I had to choose which one was better, I would definitely choose that one. The fourth example is log base what of 2x equals negative 1. What number is actually invisible right down over here? We have an invisible 10 because this is the common log. Log base 10, or common log, of 2x equals negative 1. This is an example that's going to require us to use the other rule. We said we have two rules that we're working with today. When x is in a logarithm, use an exponential equation. That means we need to change this into an exponential equation. It's already set up pretty nicely for us. Log base b of x equals y. Now we're just going to change this, if you remember, into the other form. B to the y equals x. 10 to the negative 1 equals 2x. We're trying to solve for x and get x alone. I do want to take care of this side first. How do I rewrite 10 to the negative first power? 10 to the negative first power is the same as 1 over 10 to the first power. And that right there is still equal to 2x. 10 to the first power is 10, so 1 over 10 to the first power is just 1/10. Not much to do there. Instead of dividing both sides by 2 and creating a complex or compound fraction over here, I'm going to multiply both sides by 1/2. I'd rather just have another fraction being multiplied in here. 1/2 times 1/10 is 1 over 20. 2 and 1/2, inverse operations, multiplication by 2, division of 2, and we're left with just x. So our answer to this, x equals 1 over 20. Now whenever we solve a problem that started off with log in it, it does require actually one more step. The other step is that we have to check that our answer is in our domain. Log's domain is not all real numbers like an exponential, so it does require some checking. The fastest way to check is take whatever it is that your problem has you take the log of, and set that greater than 0 and solve for x. If you think about the graph of log, x is always greater than 0. Really, whatever you're taking the log of is always greater than 0. If my log was something like log x plus 4, that would have moved the graph left 4. That would be at negative 4. So x plus 4 has to be greater than 0, which means x has to be greater than negative 4. And again, it still makes sense. If I wanted to solve for x here, again, remember, we're finding the domain. In order to get x alone, I'm going to divide by 2. X is greater than 0 divided by 2 is 0. So that means that we can have anything from 0 to infinity as our answer. 1 over 20, is that between 0 and infinity? Yes. So this answer is fine. So recap, when you're solving an equation that started off with log in it and you get an answer, you need to check if that answer is in your domain. To find the domain of a logarithm, you take the thing that you were taking the log of, in this case 2x, and you set it greater than 0. From here you solve for x. That will give you your domain. Any answers you get must be on that interval. We'll see more examples like this in a second. This example does not have parentheses around x plus 4. That means that the log base 2 is only being applied to the x. If there are no parentheses there, you can't just make them up. We are solving an example that has the x inside of the logarithm. When x is in a logarithm, use an exponential equation. But before I can change this to an exponential equation, I need to isolate the log base b of x. That needs to be alone first. What do I need to do to get that alone? Subtract 4 from each side of the equation. Log base 2 of x equals 4. Log base b of x equals y. B to the y equals x. 2 to the 4 equals x. Now we're basically done. X equals whatever 2 to the 4th power is. 2 to the 4th power is 16. Is this answer in our domain? What is the domain of this example? You take whatever it is you're taking the log of, set it greater than 0. Solve for x, we're already done. X is greater than 0. 0 to infinity. Is 16 on this interval between 0 and infinity? Yes. So this answer of 16 is good to go. This example is very similar to the last example. The main difference is here we have parentheses around the x plus 4. Log base 2 of x plus 4 equals 8. In this case, the log base b of x is already isolated. This whole thing right here represents the x in that expression. How do we deal with something like this? When x is in a logarithm, use an exponential equation. So 2 to the 8th equals x plus 4. Two to the 8th power is how much? 256. Last step to get x alone, subtract 4 from each side. 252 equals x. Is this solution in our domain? We take x plus 4, set it greater than 0. If we subtract 4 from each side, we will get x is greater than -4. If you need to draw it on a number line before you make it into interval notation, go right ahead. Here's -4. And the interval notation for our domain is from -4 with a parenthesis until infinity. Is 252 within our domain? Yes, it is. So we are good to go. If you were to solve these two examples by graphing, or any of these examples by graphing, just to throw it back to what we did on Desmos and a few of the other sections, you would graph each of these sides of the equation separately as y equals. So I can do y equals log base 2 of x plus 4, and this is actually something you can graph by hand, and y equals 8. That's also something you can graph by hand. I'm just going to take a second to show you what this graph looks like. Log base 2 of x plus 4. X plus 4 moved our graph 4 units to the left. This graph does not move vertically up or down at all. So the other dashed line, if you like to draw both of them, would really be overlapping the x-axis. Over 1, up none, over the base, and up 1. That's our logarithmic function. If I wanted to graph more points, that's 1 unit away, that's 2 unit away. The base tells you what you multiply by to figure out how far away you are. So the next one will be 4 units away. Next one after that is 8 units away, and by away I mean away from my vertical asymptote. The next one will be 16 units away from that vertical asymptote. So I could keep going. The equation I also want to graph is y equals 8. Y equals 8 is a horizontal line at 8. Our logarithmic function is such a slow-growing function, like I've mentioned before. It's nothing like our exponential graph. It's so slow at growing that it won't intersect this line, which stays steady until x equals 252. That's how long it will take. Next we have 3 log base 9 of x equals 1.5. X is in our logarithm. When x is in a logarithm, we're going to use an exponential equation. We need to get rid of this 3 first, so actually going to do a couple things right now. One other piece of advice I have is anytime you have decimals in these problems, I think it would be pretty smart to rewrite the decimal as a fraction. What is 1.5 as a fraction? Anything that's something 0.5 means it's half of an odd number. What odd number is 1.5 half of? 3. So it's 3 over 2. Next, this 3 is being multiplied by the log. We want to get rid of it because we're trying to isolate log base b of x. That means we're going to divide both sides by 3. When you already have a fraction on this side, instead of dividing by 3, we can multiply by what number? 1/3. Log base 9 of x equals that 3 and that 3 right there reduce, and we're left with 1/2. Now that the log base b of x is isolated, we can use our exponential. B to the y equals x. What did we say the 1/2 power is the same as? The 1/2 power is the same as the square root. X is equal to the square root of 9. And what is the square root of 9? 3. Is 3 in our domain? Anytime you have just plain log of x, doesn't matter what the base is, if it's log of x, nothing's going on with this x right over here, the domain will be from 0 to infinity. Is 3 between 0 and infinity? Yes. 2 times log base 4 of x plus 1 equals 5. We're solving for x, and this time x is in a logarithm. And when x is in a logarithm, use an exponential equation. We do need to isolate the log base b of x portion first. That means we need to get rid of this 2 coefficient. We're going to do that by dividing both sides by 2. Log base 4 of x plus 1 is 5/2. Now we change our form, because when we solve a logarithm, we use an exponential. B to the y equals x. It's not just this x, this whole thing represents x. 4 to the 5/2 power. Make sure when you write things like this, you make sure that the 5/2 is clearly an exponent, that there's no question about it, that it doesn't get really large and look like 4 and 5/2 or 45 over 2. You want to know that that's definitely an exponent. Equals x plus 1. Now, if we weren't able to evaluate 4 to the 5/2 simply, you would just subtract 1 from each side, and you may write it as -1 plus 4 to the 5/2 equals x, and you might call it a day. But we can evaluate 4 to the 5/2. We need a swap opportunity. We're going to swap this 4 out for a prime to a power. What prime to a power is equal to 4? If you were thinking 2 to the second, then you were correct. Properties of exponents. When you raise a number to a power, and then raise that whole thing to a power, what do you do with your exponents? If you said you multiply them, then you're correct. What's 2 times 5 over 2? This 2 is really over a 1.
You could do it the long way and do 2 times 5, get 10, 1 times 2, get 2, 10 over 2, and get 5. But we like to think smarter, not harder. Let's just reduce, and that just leaves us with 5. Negative 1 plus 2 to the 5th is x. 2 to the 5th power is 32. Negative 1 plus 32 is 31. As long as 31 is in our domain, our answer is 31. Is 31 in our domain? To find the domain, we set x plus 1 greater than 0. Since x is greater than negative 1 represents the domain from negative 1 to infinity, and 31 is on that interval, it is between those, that means 31 is the solution to this equation. Hope you like these examples. Hope that they helped you out. Hope that you wrote down these two main rules over here at some point. It's really what it comes down to for all of these problems.